We'll discuss the Coda distributed file system in this lecture. So a distributed file system typically has a lot of client caches. So we'll discuss that in some detail. Then we'll discuss the semantics of the file system, finally replication. So first we will discuss the broad overview of the design and then the details of the design and give a little bit of an introduction to the evaluation. So of course the detailed evaluation will be there in the paper. So in this presentation we'll just be covering the main points. So a distributed file system is something like this. So it is very much similar to what many of us would have seen in our universities, that there would be a centralized file server and there would be a set of clients. So a client can be a laptop, a desktop, doesn't matter. So all of them would be connecting to this file server and they would, nothing would be stored on the laptops or on the desktops. So these machines are also known as client machines, and the client can be really thin. So these are also called thin clients, which means that it's just about a monitor with a very bare bones processor. So the thin client can also connect with the file server, and the entire set of files will be resident on the server. It's just a small part will be brought in, whatever the user wants to work on, and after the user is done, they get transferred back to the file server. So the advantage here is that I can do something on my laptop. I can disconnect it. I can then go to, let's say, some other machine. Let's say I can go to a desktop machine. Then I can connect that to the file server. I'll immediately get back the same state of files that I had left when I was working on my laptop. So it's like a large virtual hard drive that we want to implement, right? The same set of files seen across all of these machines. So of course, all of these machines in this case are the clients, and we need not have a single server. So we actually can have a set of servers, and so they will be storing replicas of the files, so that if one of the servers fails, the rest of the servers can take over. So Coda is one such large-scale distributed file system. So it provides a very high level of resiliency in the sense that so it's not a single server, it's rather a set of servers, and it tolerates server failures by having a lot of replicas. So the replicas ensure that if one server is down, the rest of the servers can serve the request to the client. And furthermore, it's possible, it allows for disconnected operation, which essentially means that if I have connected a laptop to the server, and let's say I decide that I'm connected via a network connection, and let's say I drop the wireless connection. So then I can still continue to work on my laptop with whatever files I have cached locally, and then once I reconnect back, so once let's say reconnect back, then whatever changes I made are synced with the server. So it's rather efficient and easy to use. And of course, all file server systems have to provide something called location transparency. So location transparency basically means it doesn't matter where you physically are. So I can take my laptop, go to another, say this is the globe, I can start from, let's say, South America, right? And then, sorry, I have a bad drawer. And then from there, I can go to Japan. And then I can plug in my laptop and it will get back the same set of files. So the location doesn't matter. So there are two kinds of very basic file systems, NFS and AFS. Most university campuses have NFS, where there is one central server and all the home directories of students are mounted from NFS. The other is the Andrew file system, which is also reasonably popular. So Coda extends the Andrew file system, AFS. So it arose out of AFS primarily because the AFS versions at that time did not really provide the amount of fault tolerance and data availability that Coda actually needed. So what we know by the CAP theorem is that if we want reasonably high data availability, if we also have to want to be reasonably tolerant with partitions, then our consistency has to come down. So these are some of the difficult decisions that designers had to make when they were actually designing Coda. All right, and so this was a kind of tough decision for them, and we will see what were their decisions and what were the trade-offs in the sense that they had to make. And one more need was that when this paper was being published, increasingly laptops were becoming very popular, they were becoming very prevalent. So what was really happening in the world of laptops is that people were connecting to the file server for some time, getting a dump of the files, a view of the files, and then they were disconnecting from the network because network connectivity was not ubiquitous, and then they were working on their personal laptops. So so managing portable computers was definitely one of the issues. And furthermore, there was a need for some degree of compatibility with existing Unix-like file semantics. So this was one more of the key design decisions that was made. So when we so the first thing for us is to understand what is it that AFS provided and how did Coda extend that. So in AFS, what happens is if a client opens a file, the entire file is fetched from the server, right? So which means that if let's say I have a client over here and then I fetch a file from the server, what comes to me is the entire contents of the file, right? The entire file. That comes and it resides in the client's cache. All the read and write operations then are directed to the local file system because the file in this case is cached locally. And then when the file is actually closed, then the contents of the file are sent back to the server. All right. So what happens? So initially, if let's say this is the client, this is the server, the client sends an open call to the server. So what the open call does is that it returns the entire file. Also, what the client does is it establishes a callback with the server, which means that if there is a simultaneous conflicting access from another client, then the server will let this client know that the copy of the file that it has is actually invalid, right? So there is a concurrent modification. So in this case, the moment let's say client C receives such an invalidate message, so this process is known as breaking the callback. What the client will do is that it will essentially discard the contents of the local file. So the operation that's going there. So let's first assume that the client has not opened the file, and so the client has not opened the file, then that's okay, it'll just mark the copy as invalid. But if it is this case, where the client has opened the file, it's working on it, then it will just keep on working as it is, and once it is done, it will send a close request. So in this case, the semantics is that the last writer wins, which means that if let's say two clients, C and C dash, have opened the file at the same time and they are working, whoever commits the last, all right, whoever commits means closes the connection at the end, the write of that file stays and the other write gets overwritten. So that's the last writer wins. But assume that let's say this client has finished, client C has finished its access, the local cached copy that exists, that copy is discarded, right? But if let's say concurrent requests are alive at the same time, then of course the last writer wins. So now let's look at the caching semantics. So of course, in AFS, every client has a local cache, and in the local cache, it stores all the files that it has ever cached, right? So a file is removed from the cache only if it receives a callback broken message where it needs to invalidate a file. And why would a callback be broken? A callback would be broken at the server if another client writes to the file. So then the server, which in this case maintains state, lets client C know that a given file is not valid anymore. So how does AFS manage the caching? Well, it checks its cache on a file open call. If the file is not there, it fetches the file from the server. And if the file has been modified, then of course you need to write it back to the server after the close call. So this ensures that files can be dropped from the client's cache seamlessly. Even if it's modified, it's not an issue, because after it is closed, it's in a sense not modified anymore, because the client copy and the server copy are the same. So in this case, the file can be dropped from the client's cache. So now let's look at the semantics of Coda. So Unix has a semantics called the one copy Unix semantics, which means that modification to any byte in a file is immediately and permanently visible to every client. So the one copy semantics in Unix is okay if we are talking of a single machine, but of course it is not okay, it is not acceptable for a distributed file system. So we have the semantics of AFS1, which propagates changes of the granularity of files at the time of open and close, which we just discussed. AFS2 does something better, which we also discussed, which is that the client sets up a callback mechanism with the server, and the server is aware of the files that are cached at the client. So whenever a file changes, the server will notify the client by breaking the callback mechanism. And so this mechanism of letting clients know that look, your cached files are not valid is called breaking the callback. If there's a network partition, of course, then the client cache remains incoherent. So let's say the server is over here, client is over here. It remains incoherent and nothing can be done. So this, as far as Coda was concerned, the Coda paper, AFS2 was the latest semantics that it had seen. So now let's take a look at the Coda semantics. So in the Coda semantics, it uses a set of servers, capital S. So a client maintains a subset of servers S, which of course S is, as you can see, small s is a subset of capital S. And this set of servers small s is the ones that are actually reachable, because note that all the servers that store replicas may not be reachable. So every tau seconds, what the client does is it pings all the servers and it recomputes the set S. On an open message, what the client does is that it gets the latest version of a file from S, and so we will see there is a way to ensure that a version is the latest version of a file. If S is null, which means that if it was not able to contact any server, then the client uses its cached version if it has one. In addition, what Coda actually introduced, so we discussed, right, that availability and partition tolerance cannot be achieved with a strong consistency guarantee. So consistency in a certain sense has to be relaxed. So Coda does that, it relaxes the consistency. So it considers a file valid, the contents of a file to be valid, if it was the latest copy, right, if the file was the latest copy at some instant in the last tau seconds. So what it does is that if I were to consider this as a number line, and let's see if this is like the current time, t equal to 0, and let's this be t is equal to minus tau. Within this time, at any instant within this interval if the contents of the file were valid, and after that, so it doesn't matter, the file's contents could have changed after that, but if the callback messages, the callback breaking messages informing the client that the contents are not valid, if those messages were lost, we will still consider the copy that the client has to be a valid copy. So this essentially is a slightly a weaker version of synchrony where we are allowing errors to kind of survive for tau seconds. So errors means stale copies of files. So a file is not considered to be stale if it was modified in the last tau seconds and the modification and the message informing the client about the modification was lost. Once a file closes, the client propagates the update to all of small s. So all the servers are informed, notified, intimated about the update. So now let us discuss replication in Coda. So in Coda, we will not use S and capital S, since instead we'll give them slightly technical names, technical terms. So we will talk about the unit of replication. Say volume, which is a set of files and directories. Let that be a subtree of the shared file system. So let's call that a volume. So a volume can also be the entire file system, or it can be a large subtree of the file system. So let us call this a volume. So each file or directory within a volume has a unique ID. All right. So this is also something that AFS introduced, that every file within a volume, the moment it is created, is given a unique ID, which allows us to identify it. So it's not its path, right? It's a unique file specific ID. So part of this ID indicates the parent volume, the volume it's a part of, and the other is the file ID. So for every volume, we have a set of servers which store replicas of the volume, and this set of servers is known as the volume storage group, which can be thought as the set capital S that we were talking about. The list of servers are stored, of course, in the volume replication database, where we know what are the contents of the VSG, and every client has a cache manager. It's called Venus. So this is also the same term that AFS used. So what the client's cache manager would do is it will keep track of the subset of the VSG that is currently accessible, that is currently fault free, and that is accessible over the network. So we will call this as the AVSG, or the available servers in the volume storage group, the AVSG. So what is the replication strategy here again? So upon a cache miss, a client obtains the file from one member of the AVSG. So the client, what it does is that within the AVSG, one of the members is designated a preferred server. We will see that this is a standard approach in the sense that many proposals in this space, in the world of distributed systems, distribute the replicas among a set of servers. One among them is preferred. It is called a preferred server. So the preferred server in this case can be chosen on the basis of physical proximity or other considerations. So it is the job. So the preferred server is the one that is contacted the first. So the client then contacts the other servers on the AVSG to verify that the preferred server has the latest copy of the data. So this has to be the case. So of course, if the preferred server is outdated, then the server with the latest copy is made the preferred server. So you change the preferred server. Then similar to AFS, like AFS, we establish a callback with the preferred server, which means that if there is a modification by another client, then all the cached copies are invalidated. And similarly, upon a file close, the contents of the file are transferred to all the members of the AVSG. So also recall that this idea of this AVSG is nothing but a process group, which is something that we studied in the lecture on virtual synchrony, and some very similar concepts will come up over here in the space of a distributed file system, where we will be talking about virtual synchrony. I mean, something concept similar to virtual synchrony and how they are that relevant over here. So since we have given ourselves a window of tau seconds, almost all the events in our system, all the events in our system have to be recognized within tau seconds. So one of the events could be enlargement of the AVSG, which means that some server that was not available became available. Recall that we had a similar issue with virtual synchrony as well. So how do I detect that the AVSG has enlarged? Well, we contact missing members every tau seconds. If the AVSG expands, then it's possible that cached files may be out of date. For example, it is possible that these servers are alive and the client is fine with them, but then this server has a more recent update, and it is possible that with this there might be a conflict. So then what will happen is that for all of these files, Coda is pretty much going to drop the callback, which essentially means that if the AVSG expands, Coda will automatically assume that these files may be out of date, and this means that if any callbacks have been registered in any server, those callbacks will be removed, they will be dropped. And if the file is concurrently not being modified, then of course the cached copy will be kind of thrown out of the cache. And next time the new AVSG, which is all of these servers, will be contacted for the latest update. So one thing that you quickly need to note is that of course the idea of virtual synchrony can fit in very nicely into this. That of course virtual synchrony's main idea is anything that happens in a view remains within the view. So any message or any action that was happening in the previous AVSG, that is stopped. And definitely once the AVSG expands, the callbacks are dropped, the cached copies are invalidated. It's not necessary to do all, but of course some nuance is possible here. And then the next time that there is a request from the client, the new AVSG is contacted for the latest copy. Similarly, it is possible that the AVSG can shrink. So this is also detected by probing each member every tau seconds. And of course, it's also possible that the preferred server dies. So if that happens, then of course the Venus client system will remove the callbacks from the preferred server. In the sense, it will make a record that the preferred server will not send it callbacks, and it will try to work with the shrunk AVSG. So since the AVSG is shrinking, there is really no great fear that an update will be missed, but of course it is possible that another client might send an update to the preferred server. But of course, in that case, since we have gone with the last write wins philosophy, that will be taken care of. So what happens if there is a loss of a callback event, which means that a callback is kind of missing, the message got lost? Well, so upon a read, the client verifies the version of the file in the preferred server with that of other servers in the AVSG. So we have already seen this. So what we have essentially seen is that out of all the servers in the AVSG, one of them is a preferred server. So what the client does is that it contacts the preferred server to find if its updates are the latest. Otherwise, if that's not the case, and of course it takes the update, it verifies with the rest. If there is a mismatch, then most likely there is a missing callback. So then there is a need for some degree of reconciliation, where we will see what the reconciliation is in the next few slides. Now let us discuss the communication aspect of the design details of how exactly this is done. So given that we have seen the broad idea of the Coda system, which is basically we have a client, we have a set of servers, one among them is the preferred server, and the set of servers is known as the AVSG. There is a need that we need to read a version from the preferred server and then verify it with the rest of the servers, and essentially verify it is the most latest up-to-date data, and the writes clearly have to be sent to everybody in the AVSG. Of course, we'll also nuance this position later, but at the moment let's assume that it's sent to everybody. Can be sent to a quorum, but I'll discuss that when we discuss the Dynamo paper. So Coda uses a multicast RPC for this purpose. Instead of a unicast message, it relies on multicast messages, which most networks natively support. So multi-RPC is clearly more efficient, much more efficient, far more efficient than a unicast method, right? So this is where there is some advantage that we see from that accrues from the properties of the network, and we'll also measure this. Let us now discuss disconnected operation, which is one of the main strengths of Coda. So disconnected operation begins when the AVSG is empty, which basically means that the client is disconnected from the server. So the link between the client and the set of servers, all the servers rather, in the AVSG is lost. So this is a problem. However, the main aim was that we should not perceive this to be a major problem in the Coda distributed file system. So in this case, the client cache manager Venus tries to minimize the cache misses. Why is this the case? Well, the client has a cache which is of course managed by Venus, and what Venus tries to do is that it uses a least recently used cache placement policy, eviction policy, to ensure that all the files that are recently used are kept in the cache to minimize your chances of a cache miss, right? So this is a software cache that resides on the client. Furthermore, Coda allows the user to specify a priority for files. So the high priority files are not removed from the cache. In addition, it is also possible to annotate a certain sequence of actions such that anything that is produced as a result of these actions is marked to be sticky. For example, we can have a sticky open, right? And anything that is opened via these mechanisms gets the highest priority in the cache. Once the disconnected mode is over, which means the client is reconnected, so which means one of the servers in AVSG is accessible. For each modified file, the updates are propagated to the servers in the AVSG. So what the client does is it takes a look at all the modifications and it propagates these modifications to the servers in the AVSG. And in the case, so for a file, of course, it's easy. It's treated as a normal write. But for directories, it is kind of hard. And so we'll discuss this slightly later. But also another thing is that there might be conflicts, in the sense we might be dealing with concurrent writes. So in this case, what a server does is that it provides a temporary home for storing the client updates. So this is referred to as a co-volume, which is essentially a space within the server where it is like this one directory where all the conflicting files are stored, such that they can be reconciled later. This is very similar to the lost plus found directory See, many of you actually take a look at your home directories, even on an NFS server, you will find a directory called lost plus found. This essentially refers to all of those conflicting files which had some issue with the server and they could not be automatically reconciled. And so in this case, they are kept in the lost plus found directory. So this means that the client can resolve all of these updates at a later point in time. So when a user voluntarily disconnects her laptop, she essentially relies on the large file size, which and then whatever writes that she does has to be resynchronized at a later point in time. Now let's look at the most important aspect of Coda, which is conflict resolution. So when a conflict is detected, Coda will try to automatically resolve it. So what we will see is that conflicts on files are easy to resolve. It's also relatively easy to resolve conflicts on directories. But there are three kinds of conflicts in directories which cannot be automatically resolved. One is, let's say, an update conflict. So this is where the status of the same object is updated differently in different client partitions. For example, this can refer to the security settings. So in this case, it is possible that the access control of a certain file is changed in a certain manner on this client and in a different manner in another client. So this would be an update conflict in a directory. We might also have a remove update conflict where a file is removed in one partition and updated in the other. Also a name conflict where two files, of course, with different contents are created. So all of these things have to be kind of resolved manually at the level of the user. So Coda has specialized repair tools that allows the user to repair these conflicts, fix these conflicts. So the user can see all the replicas that are there on the different servers, and these can be manually fixed. So now let's look at the replica management. So each modification that is made has a unique store ID. So this is important. So it's like a immutable history. So these are all very similar concepts as the original blockchain idea that we have discussed. That whenever any modification is made, it is essentially a new entry and it is assigned a new store ID. So this is a very common idea, a very common concept in distributed systems, that any new update is given its unique new store ID. The server maintains a history of store IDs. So the history of store IDs on server A is a subset of that in server B. Then you can be sure that B contains new copies. So Coda will consider B to have the latest version. So B in this case is considered to be dominant, and A in this case is considered to be submissive. Why submissive? Because it doesn't have all the updates and B has all the updates. So it's a useful method for files. It can be reasonably conservative for directories because, of course, in a directory we might be modifying different files without an actual overlap. But Coda uses the same more or less for both. So Coda maintains the following kinds of information. So the first thing is that for every file, it maintains a latest storage ID. So the latest storage ID is basically, you can think of it as a scalar clock, which is a combination of a PID and a counter. So this is clearly, it can be PID is like a client ID and a counter. So you can think of this as a scalar Lamport clock, and where every subsequent store ID is guaranteed to be unique, and it's a tuple of the client ID and a counter. And of course, it contains the current length of the update history, and the LSID, as I just mentioned, is a client ID and a monotonically increasing integer. In addition, the replication site contains the length of the update history of every other replica, right? So this is like a vector clock, where basically, if you would recall, a vector clock is essentially a vector where each of these elements is a count, and for the ith entry, this is an estimate of i's local clock. And the vector clock, as we have seen, is very important. It can be used to infer causality, it can be used to infer concurrency and all kinds of things. So this is a vector clock which is called the CVV. It's a version vector, and so essentially with every object, it will maintain a latest store ID, which is the latest version of the object, and also the number of updates that each replicating site has actually made, and this information will also be there in this vector clock. All right. So essentially, we are looking at the tuple of the LSID and the CVV. So let me just go through this once again. The LSID is a tuple of the client ID and monotonically increasing integer. So from the perspective of the client, this is a scalar clock. In addition, the CVV is a vector clock from the perspective of the replica servers. So here, this contains the length of the update history of every replica. So this kind of tells the servers how recent their entries are. So now when we are comparing an LSID CVV tuple for a given file, we can have one of these four conditions. So let's see. We can either have strong equality, which means that between replica A and B, the LSIDs, the last store IDs are the same, and the histories are also same. So this basically means that both of the replicas are on the same page. So their last store IDs, which are very much the last update that they have processed, that is the same. And also they have the common view of the rest of the replicas. So they are equal. Then of course we can have weak equality. In weak equality, the latest update that they have processed is the same, which means LSID A is equal to LSID B. However, right, this part is important. Their view of the world, their CVV vectors are not the same. So this is weak equality, right? So this can be that they might have just missed some updates in the past, and then the replicas have not been updated, or some messages have been lost. So that is why the CVVs will diverge. But the fact is that they still have the latest copy, because the LSIDs are the same. Then we can have dominance. So in dominance, what will happen is, of course, the LSIDs are not the same, but the CVV of A, which is replica A, for every entry is greater than or equal to CVV of replica B. So this is a typical vector clock condition, which says that A is the more recent. A clearly has far more up-to-date information than B, because the vector clock, which is CVV, for every single entry is greater than or equal to the corresponding entry of B. So in this case, A is dominating and B is submissive. Inconsistency is when three of these conditions don't hold, and this is where some kind of a resolution is required. So the resolution subsystem has to be invoked. So if there is strong and weak equality, we can say that the replicas are synchronized. In a sense, the replicas, or rather both the servers, both of the replicas are fully the same, they are fully synchronized, and they have the most up-to-date data. But of course, with the weak equality, one of the servers does not know enough about all the replicas, but that can be fixed. So if replica A is dominating replica B, then of course replica B clearly has old information which needs to be updated. Now let's take a look at the entire details of the protocol and how the state is transformed via the state transformation logic. So what are the most common operations in a file system? File create, delete, and changing permissions, modification of permissions. So a typical Coda file operation is broken into two phases, a first phase and a second phase. So in the first phase, the client sends the LSID and the CVV. So whatever CVV it knows and the last store ID to each AVSG server. If there are no conflicts, so you don't expect conflicts generally, but you can have conflicts if, let's say, there was a disconnection and another client updated the value. So then the server essentially makes a temporary record. So this is something like two-phase commit. So this operation is very much like two-phase commit, where if there are no conflicts, the server performs the desired action and keeps a temporary record. In the second phase, so what happens is that the client, so of course from the first phase it will go to the second phase if there are no objections, if there are no conflicts. As I said, I drew an analogy with two-phase commit, which is very apt in this case. So then each AVSG site records the client's view of which AVSG sites perform the update successfully, and the vector clocks, the CVVs, are updated accordingly. So let's take a look at a far deeper look into the first and second phases. So let's look at the checks that are performed at an AVSG server in both the first phase and second phase. So this is for the first phase. So the check succeeds for files if the cached and server copies are the same and it's the same LSID, or the cached copy is dominating. So then clearly the check succeeds, otherwise it fails. The check succeeds for directories clearly when the two copies are equal. So this we have been arguing it is conservative, but Coda does follow this because otherwise we need to maintain a lot of state. Now let us see what happens if the check does not succeed. So in this case, the client pauses the operation and it invokes the resolution subsystem. This tells the client that pretty much it has a missing update or it has a stale update. So the resolution subsystem tries to automatically fix the problem, which means fetch those updates that the client didn't have and try to perform a merge. If the merge is not successful, then an error is returned to the client and the operation is aborted. It is stopped over there. However, if the client has an up-to-date copy, then what happens is that all the servers perform the action and they note the LSID of the client and commit a temporary CVV. So it is important to understand that if there are multiple servers and the client is over here, so in phase 1 what happens is that the client sends the version to all the servers and the servers then indicate if they are okay or not to go forward or go ahead with the update, and they also note the temporary CVV that the client is proposing, right? So this is the CVV, the latest CVV of the data that the client has. So this is phase 1. So in phase 2 what happens is that after the client has gotten the responses from the entire AVSG, and if there is no error, if there is no conflict, then the client sends a commit message informing the servers that they are ready to perform the update on their side, and also each server is made aware of the rest of the servers that have agreed to perform the update. So then what happens is that the server increments its own vector clock as well as the vector clocks of the entries corresponding to the rest of the servers. So this ensures that by the end of this process, by the end of phase 2, the entire AVSG, they have the same CVV for the data or the same vector clock. And why is this the case? Well, this is the case because in phase 2, if you would see over here, it records the views of each of all the AVSG sites that have performed the update successfully. So all of the AVSG sites at least that perform the update successfully are guaranteed to have the same value of the vector clock, which is the CVV in this case. So, a further explanation of this. So, each responding server augments CVVI, and the client sends this to all the servers as we just discussed. And in phase 2, the tentative CVV is replaced by the final CVV. And so the aim is that by the end of the phase 2, the AVSG has the updated data as well as it has the updated CVV for the data, and all the replicas pretty much have the same CVV after the end of phase 2. So, if there is a conflict, then the Venus file system, the client file system manager, does a force operation where it tries to attempt a merge, particularly transfer file contents from a dominant to a submissive site. And so in this case, the submissive site can either be the client or it can be a server. So it doesn't matter. Since we have a full version history, whoever does not have the updates, that is a submissive site, and updates need to be transferred. However, doing a force operation for a directory is far more complex. So we need to lock and atomically apply changes one directory at a time. And so an entire directory has to be locked and done. So basically this is kind of a hard operation, but because it is possible that a directory tree can be really deep, and this has to be done recursively. So that's the reason we do it one directory at a time. We don't do the entire tree at a time. So if let's say a new entry has to be created, what we do is we first create a stub at the server, which is guaranteed to be submissive because its CVV can pretty much contain all zeros. And subsequently, a force operation will change the status of the stub, which means give it all the updates. So why is this done this way? This is very interesting. So if we have a client and we have a set of servers, and let's say we are trying to create a new file in the directory, what I am trying to say over here is that we first create a stub in the directory for the file, which is pretty much a file with that name, but an empty entry with no contents, and which is guaranteed to be submissive to every other update. So once the stub is created, so consider this as phase 1. In phase 2, what happens is that all the updates, if the client has a dominant copy, that is, are transferred to the stub, and there is a very similar process that is followed between one server and the rest of the servers. So an astute viewer can ask that why not do both of them in the same go at the same time. So what would that mean? Well, that would imply that the entire contents are transferred to the server in one go. The problem is that if there is any node or network failure, then we might have the file in an inconsistent state, or some of them will have an update and some of them will not have an update. So it's possible that maybe this and this server have the contents of the file and this server doesn't. So to stop that, what we do is we just create a stub entry that at least indicates to the server that look, a file with this name exists, and then in the second stage all the updates. So creating the stub is very quick, right? These are very quick short messages that can be sent in a single RPC. Once all of them have it, the process of transferring the file can then be done later, and even if let's say this process gets interrupted, then at a later point of time, if this server has all the updates, it will see a submissive entry and transfer the updates to this server. So this increases the reliability of this, the robustness of this process. So we also have repair and migrate operations. So a repair operation is used to fix inconsistent updates. So as we said, whenever an inconsistency is detected, the file is moved to a co-volume, and so in this case they are stored there for the user to manually take a look. So all accesses to inconsistent objects fail, and so basically in this case we wait till the conflicts are actually resolved. So coming to the implementation, well, this was implemented on IBM workstations. So when it was implemented, 12 megabytes of main memory was a lot, but of course nowadays it's nothing. Even smartphones have much more memory than that. But for those days, 12 megabytes of main memory and 70 MB of hard disks was all that was there. And so the servers, so this is what the workstations had, and the servers had 400 megabytes of disks. And the Andrew file system benchmark was used, which is essentially 200 KB each, 70 files. And there are a set of operations: read, write, read directory, scan directory. So it's a mix of operations. And for single site transactions, the Camelot transaction engine was used to ensure that operation on a single site happens atomically. So 4 configurations were studied. No replication, which means there's no additional server. So it's like this is the baseline AFS overhead. So the time overhead per operation just increased by 21%. So the nice thing about Coda, which was really appreciated at that time, and this is why this paper remains a classic, is primarily because the additional overheads with extra servers is a kind of minimal. So it increases to by 1%, 4%, and 5% respectively with additional servers. And the main reason is that we use an RPC based mechanism. Updates can be lazy, we maintain versions. So the critical path in a certain sense is actually not lengthened. And since many of these operations are not really very network dominated, this doesn't turn out to be an issue. So for AFS, the elapsed time for different load units. So where of course we are defining a load unit as the unit, the load generated by 5 users. So basically the total time for running the benchmark was roughly 400 seconds. And this increases to 400 to 650 seconds as we have seen across loads for 1 to 10 load units. So it increases quadratically. So it's not a linear increase, it's like a quadratic increase like that. So as we increase the load, Coda does increase superlinearly, and the main reason being that it puts a higher load on the network synchronization, server management, version management, migration, etc. But nevertheless, this is a very scalable file system, and this is why this paper has remained a classic. Then we will discuss the effect of multicast and unicast. So if unicast is used in an iterative fashion, the network load in terms of packets increases linearly from 5,000 to 60,000 across load units. And for multicast, of course, the number of packets reduces. And so I would advise the viewers to take a look at the paper. So the paper also talks about latencies and so on. So in general, while designing a distributed system, it's a good idea to use the multicast and broadcast capabilities of the network. So this was the reference IEEE Transaction on Computers 1990, a very old paper. But this paper has inspired successive generations of distributed file systems. And many of today's file systems owe much of their origins to the Coda paper.